Hey guys, welcome back. So now we're in chapter 3.2, biosignaling. So I would say this is a relatively important one. So let's get into it. So first of all, we need to talk about ion channels. Now, I hope these are very, very common to all of us, but let's go over it anyways. So facilitated diffusion. Okay, you could think about facilitated, right? Meaning that you need help. So you need ion channels to help ions move across membranes, okay? Very simple definition. Try to make that as simple as possible, right? Ion channels help ions move across membranes. Now, you may be wondering, like, why do ions need help? Well, it's due to their charge. It really is harder for charged molecules to move through membranes due to lots of different factors, polarity, size, or whatever. More of the story, you need ion channels for ions to move across membranes. Now, we have a few different type of ion channels, right? Ungated, pretty easy, right? If you don't have a gate on something, it's always open. An example being your K plus leak channels that cause hyperpolarization when you have an after an action potential, okay? You have K plus leak channels, and that is what causes the hyperpolarization. Next, voltage gated, obviously voltage gated, right? So you need to be at a specific voltage, right? Quotation marks, to get a response, to open, right? To allow the ions to flow through. So again, we could use action potential as another example. If it was at negative 70 millivolts and you have your action potential, right? So once you reach a certain voltage across your membrane, then your voltage gated channel can open, okay? So ligand gated, this one's a little easier, right? So if you think about what I want you guys to think about as a ligand is a key. So you need a key to open the door, right? So ligand gated ion channels, you need a key for the ions to go through. So we have enzyme linked receptors. So these are three different membranes spanning, three domains spanning an entire membrane. And again, this has to do with ligand binding like we talked about before. And a pretty important example would be this one here, which are RTKs. Definitely just know that they dimerize, okay, very important. And then they autophosphorylate. Very important. RTK is very, very important. I can't stress it enough. And another very, 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 very important is G-coupled protein receptors. I mean, if you don't know these, I would be like, don't even take the test, honestly. So a few things you need to know is there's 7 transmembrane domains using G proteins, okay? G, like GTP, GDP, right? Okay, so when that is why they're called G protein receptors. It's because they use G proteins. So these three, again, this is another thing. Now, I feel like this is good knowledge. I haven't got a specific question about this, but once I understood this concept, it all made more sense to me. So GS, right? Stimulating, okay? So stimulating adenosine cyclase. Sorry, not adenosine, but CAMP, right? GI inhibiting, okay? So this stops your CAMP. GQ activates phosphorylase. So you turn this C into IP3 and then DHE, and then that's going to give you increased calcium levels, okay? I would say, like, this one of all is probably the least important one, this last one here. So if that one came off as confusing, that's fine. But what I really want you guys to understand is the rest of this, right? 7 transmembrane protein, it uses G proteins, okay? Definitely, you're gonna need to know this like truly in better detail than what Capstone has. So I would definitely recommend keep harnessing this, like grow on top of this. And yeah, okay. So definitely that is a very big one. This is a good foundation for it, but definitely like look into it on your own. So next we're gonna go over protein isolation. So I'll see you guys in that video.